Oh, hi everybody. So this is our second exercise testing lecture. Today we're going to concentrate on those submaximal responses. But first of all, a little bit of recap. And the recap is on the maximal responses. So we'll have talked about this again, probably in our workshop, but this is kind of just to make sure we're all on the same page with the exercise testing. There is a reading, which is this dynamic interactions of gas exchange, body mass and progressive exercise, but there's also the prior 2019 reading from Dan Cooper, which is also relevant. So we talked about exercise testing and maximum, and you know, lots of kids don't get to maximum, and this is a nice video from my colleague at the University of Calgary. This was the HOP research study. It was with much younger children. They used treadmill testing without gas analysis, but they still did take them to maximum. This is the easy bit. Getting harder. This is a tough protocol, 16% gradient, and he's so small. Not really talking anymore. End of the test. Very slow countdown. You know, we said Dan Cooper says it, the max effort is only as good as the cheerleading team. And there's lots of reasons why kids finish a test. Did they give a volitional maximum? Well, it is their maximum. And it's hard on kids. They haven't, done anything to maximum before. So maximal exercise testing is useful, but it also has its deficits. We think about kids in adult terms. We've always looked for this plateau in, we increase work rate to a point where VO2 doesn't increase anymore, it plateaus. We know that's not true. It actually even wasn't true in the original A.V. Hill study. A.V. Hill was the researcher who put those Douglas bags on the back of the participants in the 1920s. They ran around a track and they ran faster and faster until they couldn't run any faster. So not really a maximum VO2, it was more maximal running speed. A.V. Hill actually went on to win the Nobel Prize, not for his VO2 max work, so good physiological researcher, but he himself didn't say that this was, they did plateau, but it was only because they couldn't run any faster, they weren't on a treadmill. And kids don't plateau, generally speaking, we know that. So now you ask, well, okay, how do we know this was truly a physiological maximal effort? That's not really an endpoint. Do we have to look for some other criteria? And the body obviously has an upper limit for oxygen utilization, and that is determined by cardiac output, AVO2 difference, that ability for the muscle to extract oxygen. But we need other endpoints. Now, we've talked about the supramaximal verification, and we tried it with the kids. It's pretty grim. You saw it in a video. The kids can run to maximum, then we take them off or cycle to maximum, we take them off the bike, we let them recover, then we put them back on the bike and we warm them up, and then we increase the workload above that they finished at maximum, and we see a VO2 increased. And it's just not practical to do, number one, in your average kid. So your young athletes do this well. But Cooper brings up some points in his paper. He's not a fan. He said, I don't think this is also that physiological. We get a priming effect. If you've exercised first, you've primed the muscle to be more oxidative. So when you get back on the bike, the likelihood is you can give more. So that's a problem using supramaximal. The bottom line is kids stop because they're tired, they're breathless, their legs ache. Most of the time on our bike, their butt aches. And they really have clear, obvious signs of intense effort. They're breathing hard. You know that they're getting close to maximum or at maximum. And I think for them, that is their maximal effort. We'll look at some parameters, heart rate and RER. We don't look at blood lactates, and we'll come to that in a secondary lecture that I'm going to talk a little bit about the oxidative metabolism of the child. But Heart rates, even we give these arbitrary cut points, sometimes we'll only get 185 and the kid's clearly at maximum, or 180. Sometimes we've got kids giving 200, 205 on the bike. So they're useful as surrogates. They reflect the fact that there's a little, this child is getting close to their maximum. But again, they're not reliable. They're not the same for everybody. So we generally just use the speed at which we take the test until the kids aren't able to keep up pedaling speed, whether that's 60 or 70 RPM. We set that criteria in advance. And, they pedal until they can't keep going, and then that is their volitional maximum. So maximum is useful, but it's got all of these issues related to how do we know it was a maximum? What if they weren't giving a maximum, then they come back after training and they give a better maximum? Do they really train, or are they just putting more of an effort in? So the max test is not worthless just because we don't quite know whether it's maximum, because there's all that submaximal data that we get out of the test on the way up to maximum that's actually more valuable in many ways than just the maximal parameter. So that's what we're going to do. We're going to look at how we interpret the submaximal data. So Cooper does this really nicely in both the papers. He shows that, first of all, the ventilatory thresholds, we'll talk about that in a moment, gas exchange thresholds are really valuable, but there is also slopes that we can calculate that tell us different things about the system. And the steepness of the slope tells us about the capacity of the system. So we can consider the interface between the heart and the muscle, the cardiac muscle efficiency. If we look at the slope between heart rate and work rate, we can take a look at cardiac function. We get a surrogate for stroke volume in oxygen pulse. That's oxygen uptake divided by work rate, or we can plot this as a slope. And we can also look at lung function by plotting the slope of ventilation over VCO2. So these are really valuable parameters, and they start to tell us more about the system than just maximum. So the first thing, as I said, which we've done already, we look at the whole test. Let's just plot VO2 over time. Let's plot heart rate over time. Remember, when you've got your Excel file, you've got warm-up, test, recovery. So yes, plot that warm-up, test, recovery, the whole data when you first just eyeball the data. But also remember that when you're starting to plot the slopes, you want to only plot the exercise test data. So you want to remove the data that are warm-up and recovery. Just save a file, delete those data. It's marked in the files, and now you get to see the actual exercise data. It's also worth plotting VO2 over heart rate because you get to see some of these relationships. There we have VO2 in milliliters on the y-axis and heart rate in the x-axis. And this slope can be interpreted, and Cooper's paper gives us some nice normals for these slopes and a great explanation again of what they mean. And this is the oxygen pulse slope, and it's telling us it's a surrogate for stroke volume, and this stroke volume to relationship with exercise changes with age. So it also changes with fitness. So I want to start with gas exchange thresholds. That's where we started in the workshop. I want to just go through the theory of what these are and how to make sense of them. You now know how to plot them. These are our anchors. And they're two anchors, and they're very useful thresholds. What do they mean? You've learned this already in exercise physiology, but I'll just go over it. They really indicate cut points or changes in the energy systems. And so the ventilatory threshold 1 is that change from purely oxidative metabolism into that more glycolytic mix. And our ventilatory threshold 2 is really that switch to anaerobic, all out, give it to the end of the test section of the data. So we call these different things. Ventilatory threshold 1 is called anaerobic threshold or lactate threshold. We don't use lactate, we're using the gas exchange data. So gas exchange threshold or ventilatory threshold is useful, and you can also call it anaerobic threshold. The ventilatory threshold 2 is often called the respiratory compensation point. So ventilatory threshold 1, our gas exchange threshold, is really useful in performance. So that threshold indicates a pace that you can go at, whether that's cycling or running, without fatiguing. So you can work at that threshold. If you go above that threshold, you're going to start to fatigue. And this is a great threshold because it responds to training. So you can increase the threshold, which means you can run at a faster pace without fatiguing. So very, very useful anchor for performance. Have you done a max test? If you have, go back to when you did the max test. How did it feel? First 6 minutes felt fine. And then it starts to get harder. And it's usually around the anaerobic threshold point and above. You start to think, oh, okay, feeling it now. Breathing harder. This is grinding on my legs. Then towards the end of that test, all hell breaks loose. And you start breathing like a crazy horse. Your body's desperately trying to buffer the CO2. There's not a lot of time left between that and maximum. You're really sustaining the end of this test anaerobically. Your tank is empty. And that point is the respiratory compensation point. And as I said, max comes shortly thereafter. So how do we identify these? Well, there's many ways and many variables that can be used to identify these points. We'll have done two. We'll have looked at the ventilatory equivalents and the V-slope method. So if we take a look at the data, we can just plot ventilation over VO2 and just look at the lie of the land, visually determine using different plots. You can see that there's a nice linear relationship, but at some point, ventilation starts to increase quicker than VO2 and we get a steeper slope. So we can eyeball at that point, that breakaway point. Yeah, that looks like ventilatory threshold 1. The most common way of doing this is to look at our ventilatory equivalents. Here we have our ventilatory equivalent for oxygen and our ventilatory equivalent for CO2 plotted over VO2. We've been plotting it over time, but you can plot it over VO2, you can plot it over work rate. And you can see that there's, again, a clear breakaway at different points in the test. And again, these are going to be used, and we're going to interpret those to determine our ventilatory thresholds. So let's think about VT1 first. So VT1, when we start the test, the easy part, ventilatory equivalent for oxygen declines. And then at some point it starts to rise. And at that point when it's rising, ventilatory equivalent for CO2 is still declining or has plateaued. And that is VT1. This is an eyeball method. You are just visually determining this from your plot. This time it's plotted over power output, but we can plot it over time. And we can find the power output and the VO2 at that time point. Or you can do it over power output and find the time and the VO2 at that point, or the heart rate. So x-axis doesn't matter that much, depends how you're going to use the data. So we're looking for that inflection point, that point where ventilatory equivalent for oxygen starts to rise without a rise in ventilatory equivalent for CO2. That's the point where it starts to feel hard in a test. So now there's some buffering of CO2, you're working a bit harder. Ventilatory equivalent for O2 is rising quite rapidly. And then at some point, we've got this stabilization in the ventilatory equivalent of CO2, but then there's that point in the test, the all hell breaks loose point, when suddenly your ventilatory equivalent for CO2 really starts to break away. And you can't really sustain work for much longer. And at that point, when both are rising, that's our RCP point. We'll have done this. We'll use lines on your Excel, draw lines to visually eyeball this point. You need to be careful doing it. There is a second method we've done, which is our V-slope method, which is less eyeball and more specific because we plot regression lines to do this. So in our V-slope method, we normally plot carbon dioxide on our y-axis, oxygen uptake on our x-axis, but we have to plot it, as we said, in two different data series. So we go back and we find that ventilatory threshold 1, find what time that occurred, and your first series will take that data maybe a minute after that. Your second series would take a minute before that to the end of the test. And then we can just add trend lines, and where they intersect is ventilatory threshold 1. This is more reliable, but sometimes hard to find. So I would take this over the eyeball ventilatory equivalence method, and we can generally speaking get a better measure of ventilatory threshold 1 using this method. Then we can interpret it using running speed if we were working with a treadmill, wattage if we're working on a bike, heart rate. All those things now become anchors for training. So I know if at that heart rate you were at ventilatory threshold 1, or at that wattage you were at ventilatory threshold 1, I want you to train at 90% of that. So I can give a precise wattage for training, and I can monitor heart rate. We can also express it as a percentage of peak VO2. So if we calculate this value, we can find the VO2 at that value, divide it by peak times by 100, we get a percentage of VO2, and then we can interpret how that child is in terms of the average. And a group in the Netherlands, I've given you this in Canvas, did a very nice job of plotting these and giving percentiles, so 3rd to 97th percentile. This is for the boys, this is for the girls, and this is just an example. 9-year-old girl, let's say she had percent peak VO2 of her ventilatory threshold 1 was like 55%. She is about the 25th percentile. That means she is below normal. She's basically a little unfit. If somebody was up here, they're very fit. The great thing about this variable is it does increase with training, so we can measure it again and see if we can raise that bar. So let's turn our attention to the slopes. And first of all, I'm going to look at that oxygen pulse, that oxygen uptake heart rate relationship. So we know that oxygen pulse, if we just calculate oxygen pulse, just divide VO2 by heart rate for all your exercise test data, then plot it against, if we had lots and lots of different maximal oxygen pulses and we plot those against peak VO2, it's a really good determinant of oxygen uptake, very, very strong linear relationship. It also has a strong linear relationship to VO2 and lean body mass. So it's a surrogate for stroke volume, and we can plot the actual slope, and it tells us about the cardiac contribution to the exercise test. So it increases with growth, as does stroke volume. And when we plot this value, this is not the value plotted, these are just, again, oxygen pulse plotted against weight and height. You can see it increases essentially with age, because that's what you're seeing when you're looking at weight and height. And it could indicate arterial venous difference, i.e. extraction of the muscle, but it's most likely, we know, to reflect stroke volume. So if we go to Cooper's work, we can see that this relationship this is in males and females at age 8 to 10, 11 to 13, 14 to 15, 16 to 18. You can see that the values increase with age, and there is a sex difference. That's the same with cardiac output, larger heart, greater stroke volume in the males. So this is really valuable. This also will increase with aerobic fitness training, so a valuable metric. We can look at that relationship between oxygen uptake and work rate. This really is telling us a little bit about that interface between the efficiency at the muscle, the peripheral efficiency. So the oxygen uptake heart rate is like that central cardiovascular control, and this is more of the peripheral work that's going on. So think about what kind of test this is. This is not the test that I've shown you that we do in the lab. This is a step test. So at every point in time, there's a step increment in work rate. It's like going up the stairs. We use a ramp protocol, which is continual increase in work rate, like the dotted line. And you can see that when we plot VO2 over heart rate, we get a fairly linear relationship. And it's a measure of that kind of aerobic output at the periphery. The more fit you're, the more efficient that metabolic engine, and the more economical you are at a higher work rate. So you would expect a very fit young person to have a better slope because they would be more efficient. So again, Cooper's giving very nicely this data. It doesn't change much with age, but likely is indicative of fitness. And then we're going to turn to the lung, and we can take a look at the way in which ventilation relates to ventilatory to VCO2. So we know that kids, particularly younger children, breathe more than adults for a given increase in metabolic work. In other words, they have a higher ventilation for a given work rate, and they also have a higher breathing rate and tidal volume to get there. So we don't really know why. There's lots of reasons. It's likely that they have maybe have a slightly lower arterial CO2 content because they have a larger dead space to tidal volume ratio. There's some thought that they're more sensitive to CO2 because they have a smaller storage capacity for CO2. Well, we can see these times where VeVO2 is disproportionately increasing, that ventilatory threshold 1 to VeVCO2. And also at the end of the test, we see this really rapid increase where that there's a huge increase in breathing to compensate for fatigue to blow off CO2. So to really understand the gas efficiency exchange, what we do is we only take the data up to RCP. So we have to plot the data below RCP because we've got this just complete offshoot of ventilation after RCP. And we plot again, this is in litres per minute against litres per minute. We are plotting the exercise data up until that respiratory compensation point, which we have to have identified. And then we can find the slope in this relationship. And this really is a measure of the efficiency at the lung. That's what this slope is reflecting. And that's important, again, from a performance perspective. And so you can see that this slope declines with age. There's not really a sex difference, but again, you might see a difference with exercise training. So as the lung develops, you start to breathe deeper and deeper and slower. So you get this change, this lowering slope. In an adult, a slope of 33 would be super inefficient, but that's not an adult, this is a child. And in fact, in an adult, that would reflect ventilatory compromise, but it's just this immature lung. And it's likely because also that the anaerobic capacity comes with age. Children are highly oxidative, and we're going to talk about that in the next segment. And I'm going to break this up and stop here and go back to that in the next segment.